All right, we're diving into a pretty wild molecular mystery today. I want you to imagine two molecules. They've got the exact same chemical formula, same atoms, connected in the exact same order, but somehow they act like totally different things. It's a real puzzle, and it's all part of this fascinating world called optical isomerism. So that's the big question, right? How can two molecules, perfect mirror images of each other, mind you, have these completely different personalities? Well, to crack this case, we need to start looking for clues. And our very first clue, believe it or not, comes from a very, very special kind of light.
Okay, so to get to the bottom of this, we can't just shine any old flashlight on these molecules. Nope, we need a very specific tool for the job. And that tool? It's a special type of light. We call it polarized light.
You know what's funny? Even a single, simple beam of light is way more chaotic than it looks. A light wave is actually vibrating in pretty much every direction at once. Up and down, side to side, diagonally, you name it. It's a jumbled mess of vibrations all happening at the same time.
So to clean up that mess, we need to send the light through something called a polarizer. Now, the best way to picture this is like a fence with only vertical slats. The light waves that happen to be vibrating up and down can sneak right through the gaps, but all the other vibrations, the side-to-side ones, the diagonal ones, they just get blocked. And what makes it out the other side? A nice, clean, orderly beam of light that's vibrating on just one single plane. That's our polarized light.
All right, now we've got our special tool, this plain polarized light. So it's time to put our mystery molecules to the test. We use this nifty device called a polarimeter, which basically just lets us shine our special light beam right through a sample of the molecule we're curious about.
So what are we hoping to see? We're looking for something called optical activity. And all that really means is, does the substance have the power to grab that nice, neat plane of light and give it a twist? And the test itself is super straightforward. If the light goes in vibrating, say up and down, and it comes out still vibrating up and down, well, then the molecule is optically inactive. Nothing to see here. But if it comes out vibrating at a different angle, if that plane got rotated, then bingo, we've found ourselves an optically active molecule.
Now this twist can go one of two ways. If the molecule rotates the light to the right, kind of like turning a dial clockwise, we call that dextrorotatory. For short, we just use a little D or a plus sign. And if it twists the light to the left or counterclockwise, you guessed it, that's levorotatory. And we use a little L or a minus sign.
Okay, so we've seen this really cool effect, but we still don't know why it happens. This ability to twist light isn't just some kind of magic trick. It actually comes from a very specific and honestly, a really fascinating detail hidden inside the molecule's own structure.
So what exactly is it about a molecule's blueprint that gives it this strange power over light? The entire secret? It boils down to one special kind of atom.
And that secret ingredient is something we call a chiral carbon. Okay, so think about carbon. It loves to form 4 bonds. Now, if every single one of those 4 bonds is attached to a completely different thing, a different atom, a different group, then that carbon atom is officially chiral. A great way to think about it is like your hands. They're mirror images, but they're not identical, right? That's chirality.
Let's take a look at a real-world example. Lactic acid. That's the stuff that gives yogurt and sourdough that tangy flavor. If you look at its central carbon atom, it's a textbook case of a chiral center. It's bonded to 4 totally different groups. And it's that unique asymmetric setup that gives it the power to mess with polarized light.
All right, let's pull all our evidence together. We've got molecules that are mirror images of each other, we've got our special tool, polarized light, and we found the culprit, the chirocarbon. I think we have everything we need to finally crack this case and give a proper definition for optical isomers.
So here it is. Optical isomers are compounds that have the exact same formula, but they rotate polarized light differently. And why do they do this? Because they have a chiral center. This creates 2 versions of the molecule, a left-handed version and a right-handed version. And here's the kicker. One hand will twist the light to the right, and its mirror image twin will twist it to the left by the exact same degree. It's perfectly balanced. Now here's a super important little detail that can be a bit confusing, so let's clear it up. Those lowercase d and L letters, they tell us what we actually see in an experiment, which way the light rotates. But you might also see a capital D or L used. That's totally different. That notation is describing the actual 3D arrangement of the atoms in the molecule, not what it does to light.
So the big takeaway here is this. Just because a molecule has a D in its name doesn't automatically mean it's going to be dextrorotatory or D.
One label is for the physical structure, the other is for the experimental result, and you can't assume one from the other. Okay, I know this might all sound a bit abstract and academic, but this whole handedness thing, this chirality, is absolutely critical for life as we know it. So let's look at why, by checking out a few molecules you've definitely heard of.
First up, glucose. You know, the main fuel for our bodies. When you draw it out as a straight line, you'll find it has 4 chiral carbons, 4 of them. But here's the thing. Glucose doesn't usually hang out as a straight line. In nature, it curls up to form a ring. And when it does that, it actually creates a 5th chiral carbon. That one little change has massive implications for how our bodies can recognize and use it.
Now, let's compare that to fructose, the sugar you find in fruit. It only has 3 chiral carbons. See the difference? These seemingly small changes in the number of these special carbons lead to enormous differences in how they function in biology. So here's the bottom line. The handedness of a molecule, which is all determined by its chiral centers, dictates its job in the natural world. It's the ultimate lock and key system. For instance, your body's cells have the perfect lock to use the right-handed version of glucose for fuel. But if you give it the left-handed version, it's like trying to use the wrong key. It just doesn't fit. It's completely useless to us.
And that brings us to a really fascinating final thought. If our bodies are so incredibly specific, built to recognize only one hand of a molecule, what does that mean for pretty much everything else? You know, how might the handedness of a drug molecule change how it works as a medicine, or how we perceive the taste of food, or even the smell of a flower? It's a puzzle that goes way, way beyond the chemistry lab and into our everyday life.